I want you to picture the open ocean for a second. It's huge, it's powerful, and it is completely, utterly unforgiving. Out there, you're in charge of a vessel weighing thousands of tons, and the only thing standing between a safe trip and total disaster is good judgment, years of experience, and a shared set of rules with every other ship out there.
Yeah, out on the open sea, there are no stop signs, no traffic lights, not even any lanes painted on the water. The number one job, the absolute top priority for any sailor, is incredibly simple. Do not hit anything. It's the most basic rule of seamanship, and well, the stakes don't get much higher.
And this is not a new problem. The Greek historian Thucydides pointed this out, a little sarcastically, more than 2,000 years ago. It's always been a bad day. But over all those centuries, we humans came up with a really elegant solution to this chaotic dance of steel on water.
That solution is the International Regulations for Preventing Collisions at Sea. Now that's a mouthful, so pretty much everyone just calls them the COLREGs. You should think of them as a universal language of the sea. They allow captains from totally different countries speaking different languages to know exactly what the other's going to do. It's all about clarity.
The core idea here is actually beautiful in its simplicity. See, in most situations between two ships, one of them has the job of maneuvering to avoid a collision. That's the giveaway vessel. The other ship, its job is to be predictable. It has to maintain its course and speed. That's the stand-on vessel. Let's see how that works in practice.
So, first up, we have Rule 13, Overtaking. This one's easy. If a faster ship is coming up from behind you, from a very specific angle, the rule is crystal clear. The responsibility is all on them, the overtaking vessel. It is their job, 100%, to stay out of the way.
And just look at the language from the rule itself. There's no wiggle room, no ambiguity. It says, shall keep out of the way. That's an order. It's not a suggestion. And it's that kind of clarity that makes this whole system work.
All right, next we have the head-on situation. That's Rule 14. If two ships are steaming right at each other or almost right at each other, the rule is just as decisive. Both ships alter their course to their right, that's starboard, so they pass each other with their left or port sides facing. It's a simple, predictable little dance move that just gets rid of all the guesswork.
But then you have the crossing situation under Rule 15. This is often the most complex one. The rule says that the vessel that has the other ship on its own starboard, its own right side, is the giveaway vessel. So, simple way to think about it, if you look to your right and see another ship on a collision course, you're the one who has to do something.
And what you have to do is also laid out. Rule 16 says the giveaway vessel must take early and substantial action. Meanwhile, Rule 17 says the stand-on vessel holds its course. But notice those words, early, substantial. Those aren't numbers, right? They're concepts. They need judgment, they need experience, what sailors call good seamanship. And that brings us to the big challenge.
We're now in the age of automation. We are building ships that can navigate themselves. And these machines, they can calculate course and speed with a precision we humans can only dream of. But how in the world do you program something as fuzzy, as human, as good seamanship into cold, hard lines of code?
I mean, that's the big question, isn't it? It's what researchers are wrestling with right now. An algorithm understands math, it understands logic. But how does it understand doubt, or timing, or what looks right to the person on the bridge of the other ship?
So how do you even start to solve this? Well, a study from Cambridge University Press came up with a really brilliant first step. You translate those abstract human feelings into solid, measurable numbers. What the researchers did was define a series of ranges or zones around the ship, and each zone triggers a different level of response from the AI.
Think of it like this. When another ship enters the outer evaluation range, the AI just starts keeping an eye on it. Then, if it gets closer and enters the giveaway range, the AI knows, okay, it's time to think about maneuvering. If it gets even closer to the doubt range, the AI is programmed to act even if it's the stand-on vessel because it assumes the other guy isn't doing their job. And finally, you have the extremist range, which basically means collision is about to happen, do anything to avoid it. It's an amazing way to build a framework for machine-based judgment.
And here's where it gets really clever. Once you can define these actions with numbers, you can do something else. You can score them. You can literally create a report card to grade how the AI is doing and see if it's actually learning how to be a good seaman.
And that is exactly what they did. They created these metrics that are tied directly to the COLREGs. For example, Rule 8 says you should avoid making a succession of small alterations. So they created a score for the number of course changes. An AI that kind of dithers and can't make up its mind, it gets a low score.
an AI that makes one big, obvious course change high score. They also grade things like how close it gets to make sure the AI learns what a safe distance actually feels like.
And you can literally see the results of this learning process. On the left, that's an early version of the AI. It makes all these little hesitant course and speed changes. I mean, sure, it avoids the collision, but its actions are confusing. They're unpredictable. It gets a really bad score, a 0.74. But now look at the right. After learning from the scoring system, the AI makes a single, early, substantial course change. It's clean, it's efficient, and it's easy for another sailor to understand. The result? A nearly perfect 0.99.
This right here is the heart of good seamanship, and now it's been perfectly translated into machine logic. The algorithm didn't just learn how to avoid a crash, it learned how to do it in a way that builds confidence and makes things safer for everyone else on the water. But of course, this brings up the next big question. It's one thing for an AI to learn to be predictable, but how are these predictable machines going to interact with the single most unpredictable thing out there, us, humans? How does the person on a regular ship know what the robot ship is thinking?
Well, one cool idea from a SynTef research paper is this concept called automation transparency. The goal is just to make the AI status totally obvious. It could be as simple as a special purple light on the mast that tells everyone, hey, this vessel is in autonomous mode. Or it could broadcast its intended path for other ships to see on their screens. Whatever it is, the point is to make sure there are no surprises. And this all leads us to a pretty wild final thought. We started with ancient rules, born from centuries of human trial and error. And we ended up with algorithms that can learn and maybe even perfect those rules. An AI never gets tired, it never gets distracted, it will follow the rules perfectly every single time. So you have to wonder, are we entering an age where the machine, the student that we taught, could actually become the better seaman?